Okay, so most of the course kind of starts here. The course starts with chapter 3, but I think kind of a good place to start the course is going to be partial derivatives. So in this video, for the most part, we go over two things. Most of this video here is going to be what they call the total differential. So this is the total differential. We're just picking back up where we left off. But they go over stuff we don't have to go over, like a partial derivative. If you take the derivative with respect to one, you just hold the other value constant, so we don't really have to go over that. But it's a lot about partial derivatives, and this video is really just introducing what do we call this here? Uh, the total differential, which we know from calculus 3, but not everybody had calculus 3, so we learn it very quickly here. Okay, so we kind of skipped that. What I think we should do is we should start with the Cobb Douglas function here. Yeah. So let's just kind of quickly review what a partial derivative is. We just did it before in the homework, so we kind of did some homework on partial derivatives. This is going to be the Cobb Douglas function, and we just kind of use it to briefly review what a partial derivative is. Yeah. But they do it a little bit different. In fact, they don't. They do the exact same notation that I did. I don't quite write it exactly as they do, but if we have the partial of y, yeah, the derivative of that thing, take the derivative of both sides. It is multiply both sides by d over dx, but it's with x1 or x2, yeah. So if we take the partial, yeah, I shouldn't get stuck on math, but I can't help it. But remember, whenever you take any derivative ever in math, it is the equivalent of multiplying both sides by d over dx. So we're not going to dwell on that. I just can't help but say it once because I'm kind of a math person. Yeah. But taking the derivative of a function is the same as multiplying both sides. Yeah. By d over dx right there. So with if we have a multivariable function, and of course with a partial derivative, you can only take the derivative with respect to one variable. We don't dwell on it because it's actually easy. It's the same as a single variable calculus. It's no different. So if you take the partial derivative of the Cobb Douglas function, yeah, take the partial of that. We have to take the derivative of the x1. So it is 3 times 2 x1, yeah, cubed. I'm sorry, squared. Yeah, because we took the derivative of it, 3 minus 1. Yeah. And the x2 is held constant. So the x2 is like a number. It doesn't change at all. Yeah. So that would equal 6 x1 squared, x2 squared. That's what that would be. So if you take the partial derivative, whenever we say partial, we do mean partial derivative. If you take the partial, yes, with respect to x2 of the Cobb-Douglas function, the 2 x1 cubed is held constant, and then we have 2 x2 to the power of 1, yes. So 4 x1 cubed, it's getting a little bit rough there, x2. So we don't need a bunch. They don't really have any equations or derivatives that are difficult in this course. We learn more about the Cobb-Douglas function as we go. But the partial derivative will lead us into another term, another thing here, which is kind of the all-star of this. So let's just kind of look, some of this we can ignore. They're literally just saying that if you take a partial, it's, I say it repetitively, I don't mean to, but they just say it in like 1 or 3 paragraphs that when you take a partial derivative, we can say it very elegantly. One of them is held constant. So this is an example of a Cobb-Douglas function, which is a class of function that we will use extensively. Cobb-Douglas function have the general form, yeah. So we do want to learn what the Cobb-Douglas function is, yes, if we enlarge that. It's always like that where you have variables and all the letters are going to be constant. So it's a number, x1 to the power of a number, x2 to the power of a number. So that right there is the basic form of the Cobb-Douglas function, where a, b, and c are constant parameters and x1 and x2 are the variables affecting y. Holding x2 constant, the partial derivative of 2.1. Yes, so we just said all that. Let's kind of skip down here. What do they say here? So finally, we want to know how marginal marginally changing variables x1 and x2 at the same time affect y. For a function y equals f of x1, x2, the change delta y resulting from a small change in delta x1 and delta x2 is approximately. So it is very, very hard, I think, to understand the total differential. Yeah, I haven't really done a great job here introducing it. This right here is the total differential. Yeah, right here. Okay. So we kind of read about this now, but let me just kind of say something here. So this is a derivative, this is a derivative. Even though they look all intense, partial derivatives, they are just a slope like all derivatives. I know this doesn't really cut it, but remember we have y equals mx plus b. We don't care about the b. What is the increase in y? The increase in y is literally mx, if that makes a sense. If that makes sense, you plug in, that's the slope. If you do a change in x and multiply it by the slope, you get the change in y, yes? So this is a y equals mx, plus b or not plus b. Yeah, the change in y up or down, you just saying it again, you plug in some x value or change in x value, multiply by m, and then you're going to get that change in y. Well, with the total differential, you just have that twice. We don't really have to have kind of a sketch, but it's very, very hard to understand. This is not the all-star graph. I just tend to use it because I draw it in 3 seconds there. Yeah, the x, y, and z, or it's going to be x1, x2, and y is how we do this thing, yes. But the partial with respect to x1 is going to be slopes parallel to x1. The partial with respect to x2 is going to be slopes. Those are ones that are 0, but you have some like right here that are going to be parallel to x2. Yes, things like that. It's very hard to convey and illustrate the idea that I'm kind of talking about here. But let me just kind of say what I was saying a moment ago. So if we have a y equals mx, this is it simply put. Yeah, this one thing is like a y equals mx, and this other thing is like a y equals mx. So along one axis of our three-dimensional grid, along one axis, if you plug in a delta x, this whole thing is going to give, some sort of change in y. Now we have this way, this is basically it. We just have to understand in our head, because I do agree that my definition here is not going to be that great. Yeah, but not the whole thing, not the total differential. If you just take one, yeah, understand it's literally a slope x. So if you plug in a change in x times the slope, what does that equate to? It doesn't have to be up, it could be down, but it's literally a vertical height. It's the change that we go up or down. Okay, so we have a second one. We have a second one this way along the x2. So if you plug in a change in x2 times its related slope, what is that? It's another, yeah, delta y. And you could have some up and a lot down, which does what? It equates to that much down or something like that. But that's what the total differential is. So if this is it for the total differential. If this piece is like a change in the up and down, which it is, and if this piece is a change in the up and down, where positives and negatives obviously do count, you go up or you go down, then if you just add them, that's the actual change in y. So the change in one with respect to x1, the change in the other with respect to x2, add them, and they call that the total differential there. So that's about it for the total differential. Uh, there's a couple of things here. So we have the total differential. We're going to get back to this in the next video. Even though I can talk very elaborately, we really only have two things, like I said in the beginning. There's the total differential, and that's going to lead in a very, very basic concept that we use to optimize. We do this in the next video. So we continue with the total differential, and basically, where is it all going? I'm sorry, I'm not there yet. Eventually, we're trying to, this little guy here, which is just the slope of a two-dimensional graph, it's leading up to that, hopefully, in the next video that is derived from the total differential.